Hey guys, welcome back to Chapter 6 with Mrs. Stroh. We're still on quadrilaterals, four-sided figures. So far we know about parallelograms, special kind of quadrilateral. Today we're going to look at a subcategory of parallelograms, which are the rectangles. We'll look at their properties, use those properties to solve for parts of rectangles, and then determine whether a parallelogram is more specifically a rectangle based off of its properties. So here's our quadrilaterals family tree. We've gotten it started in our math journals. We started with parallelograms, and here's what we know about parallelograms so far. All of these you have listed in your quadrilateral family tree. We also have it illustrated in there as well. But these properties are going to carry to these other subcategories of quadrilaterals and subcategories of parallelograms that you see here in the parallelogram box. Since a rectangle is a special kind of parallelogram, what we're talking about today, all of these properties of parallelograms are also true of any rectangle. So we're not really going to copy those again because since a rectangle is a parallelogram, those things are automatically true of it. But we are going to add a couple of new special properties that are specific to rectangles, and we're going to figure out exactly what those are. So as you may already know about rectangles, a rectangle, here's its definition, is a parallelogram with four right angles. You know that rectangles have four right angles. That's one of the new key characteristics of a quadrilateral that is a rectangle. It's a parallelogram, but it also has four right angles. So that's something that we could add into our family tree under rectangles. So by this definition, a rectangle has four right angles. That's the key thing starting out. And because it is a parallelogram with four right angles, it's also got those properties of parallelograms with sides that are congruent and parallel, opposite angles are congruent, and the consecutive angles are supplementary. All of that's still true of rectangles, but there's this new special property of four right angles. Another thing that is specific to rectangles is their diagonals. Since a rectangle is a parallelogram, we automatically know that its diagonals are going to bisect each other. That's true of parallelograms, so it's also true of rectangles because they're a subcategory of parallelograms. But another thing that's extra special about the diagonals of rectangles is this. Their diagonals are congruent, so we can add that to our family tree under rectangles. The diagonals are congruent, and because of that, there's a couple theorems or implications that come from that property that we can use. The first one is, if you know a parallelogram is a rectangle, then you know its diagonals are congruent. So like you see in the diagram here at the bottom, JKLM, that's a rectangle because we see it has four right angles. So automatically we know that the diagonals JL and KM are congruent to each other because it's a rectangle. That's one theorem. Another one is if we know that the diagonals of a parallelogram are congruent, then we can classify that parallelogram as a rectangle. So if you only know it's a parallelogram starting out, but you can show that the diagonals are congruent to each other, then that's enough to prove you've got a rectangle. Okay, so knowing that diagonals are congruent kind of gives us a new property of rectangles that we can use to find missing parts of rectangles, like in the first theorem, but it also gives us a test or a condition for if a parallelogram is a rectangle or not. So here's where our quadrilateral family tree is at now. We've got all the things about parallelograms, and now we know that rectangles have four right angles and diagonals that are congruent, in addition to all of the properties of parallelograms. Those are also true about rectangles. So we've got them listed here And of course in class we'll also add an illustration of that as well. We always want to give visual representation of these things for each of these quadrilaterals as well. Now that we know properties that make a parallelogram a rectangle specifically, let's do a couple of problems where we apply those properties. So here we have a rectangular park. Oh, it's a perfect rectangle. Imagine that. And there are two walking paths. So we know that PS is 180 meters. That's one side of the rectangular park. And we know that path PR, this whole walking path, is 200 meters. We are asked to find what is the length of QT. So that's half of this other walking path. What's QT? So these walking paths in the park, those are the diagonals of a rectangle. And we know that diagonals of a rectangle are congruent to each other. So right away we know that PR is congruent to QS. Those diagonals are congruent. All right, we also know that the diagonals of a rectangle bisect each other because a rectangle is also a parallelogram and the diagonals of a parallelogram bisect each other. So that shows us that QT, the length of QT is 1/2 the length of QS because it's one of the two congruent parts of QT when it's QS when it's bisected. Alright, so since QT is half of QS, that means it's 1/2 of 200 meters, and of course 1/2 of 200 is 100. So the length of path QT is 100 meters. So if you find this rectangular park, QT right there, that's a great place to test your latest time for your speed on the 100-meter dash. All right, let me know how that goes for you. With the same rectangular park as the problem before, I want you guys to try this one. Now you know TS is 120 meters. So half of this walking path is 120. And you are asked to find what's the length of path PR, so the full diagonal of the rectangle. So using what you know about diagonals of rectangles, go ahead and find the length of PR. I'll give you just a few moments to work out on that. Have you got it? Let's double check. Length of PR is going to be twice as long as the length of ST, or 240 meters. Don't forget those units. Very important, so you know how far you're walking in the park. Alright, one other use of properties of rectangles. We're actually going to bring in another shape, your favorite shape, the shape you're already an expert about, you know every single relationship. That would be triangles. We're mixing rectangles and triangles here. Because when we look at diagonals of a rectangle, they're congruent to each other and they bisect each other. So what that means is each half of each diagonal, each of those are congruent. So each half of the diagonal in a rectangle is congruent all the way around. And what that forms for us are some isosceles triangles because there are two sides that are congruent to each other. And remember that in isosceles triangles or any triangle, if two angles opposite, if two sides are congruent in a triangle, then the angles opposite those sides are congruent. So here in our isosceles triangles, let me make that a little bigger. These are the congruent angles or the base angles. Alright, so let's go back to the problem at hand. We are given the measure of angle PRS, which is this corner of the part, and we want to find the measure of angle SQR, I'm sorry, that's this angle up here.
what's the measure of that angle? So we know one angle is 64, and this is part of a corner in a rectangular part. Remember, in rectangles, each angle is 90 degrees. So to figure out the rest of that corner, 64 plus the measure of angle PRQ, the adjacent angle, those have to add up to 90 because they're the corner of a rectangle, and those are complementary angles. So we just subtract 64 from each side to get the measure of angle PRQ, the rest of our corner. And 90 minus 64 gives us 26 degrees. So that's angle PRQ, but we want angle SQR. Fortunately, that is congruent to angle PRQ, so the measure of angle SQR is going to be the same thing as angle PRQ, 26 degrees. So you may be all tired out and done with triangles, but they are still helpful and useful to us, even though we are talking about quadrilaterals. All right, we're mixing three-sided polygons and four-sided polygons, and they are working together wonderfully to help us solve for missing parts of polygons.
All right, one other application problem. This is now a dodgeball problem. We've got measurements of the sides of a field to play dodgeball on, and we've got measurements of the diagonals. So all of those are listed for us here at the middle of the slide. Okay, we got all those dimensions. What we're asked to do is explain how the recreation center that's building this field, how they can be sure that the playing field is a rectangle. So we want to prove that this is a rectangle using the dimensions that we were given. So let's kind of blow up the field and take a closer look. All right, I'm going to label the dimensions that we are given. AB, this side is 60 feet. BC is 30 feet. CD is another 60 feet. AD is another 30 feet. All right, so far, we know it's a quadrilateral starting out because we see it has four sides. But now that we label those four sides, we see, oh, opposite sides are congruent. So that means we've got a parallelogram, at least. If a quadrilateral has opposite sides that are congruent, then that's enough to say it's a parallelogram. But we want to see if we can get more specific and show if it's a rectangle or not. So that's where those diagonals come in. We draw those into the field. We know that both diagonals were 67 feet. So AC is 67 feet. BD was 67 feet, which means the diagonals are congruent. One more set of congruent lines. If the diagonals of a parallelogram are congruent, one of the theorems that flows from that property of diagonals means that's enough to say this is a rectangle. We've got a parallelogram because opposite sides are congruent, and that parallelogram is a rectangle because its diagonals are congruent. So looking at these dimensions, that's enough to prove for the recreation center that this dodgeball field really truly is a rectangle. All right, now that you've seen some proofs of whether something is a rectangle or not in some real-world context, let's also look at how we could prove if a quadrilateral is a rectangle or not on the graph, coordinate proofs. So we're given that quadrilateral PQRS has vertices at those different points listed. And we want to determine whether PQRS is a rectangle by using the distance formula. So our distance formula, we've already reviewed in class, but I'll write it out for us again just to refresh. Distance formula, that's the big square root, where underneath we have x2 minus x1 squared plus y2 minus y1 squared. smushing the whole Pythagorean theorem into one jumbo step. That gives us the distance between 2 points, or in this case, is going to give us the lengths of the sides. It tells us something about the lengths of the sides of the quadrilateral. And because we're just given the quadrilateral part, all we know is that it has 4 sides. There's kind of 2 parts to this proof. Okay, to show it's a rectangle, the big key factor of rectangles is that the diagonals are congruent. We need those to be the same length. But the condition for this is knowing it's a parallelogram first. So we have to look at the sides first. Are opposite sides congruent? If so, then we know we've got a parallelogram, and then we can go to the diagonals and see if those are congruent to show it's a rectangle or not. So that's why there's these 2 parts here. So for part 1, when we're looking at distance, we want to know if opposite sides are congruent or not. So we kind of have to visualize PQRS on the coordinate plane. What is that going to look like? So when we label PQRS, we can see where the opposite sides are, as well as where would the diagonals be. So we want to know, is PQ the same length as SR or RS? Are those the same length? And is PS the same length as QR? We need those pairs of sides to be congruent in order for the quadrilateral to be a parallelogram. And if that checks out, then we can see, are the diagonals PR and QS also the same length? If all of those things check out, then yes, this quadrilateral would be a rectangle. But if it's not even a parallelogram, then there's no way it can be a rectangle. So Monday in class, we might be doing the distance formula to do this coordinate proof. You may do a similar problem on your homework assignment in class, but that's just kind of the setup for a coordinate proof using the distance formula. You also could do a coordinate proof using the slope formula. That's our rise over run, or y2 minus y1 over x2 minus x1. The y's give us the rise, the x's give us the run, rise over run for slope. So in order to show if a quadrilateral is a rectangle using slope, again, you kind of have to show first, is it a parallelogram? So our opposite sides parallel. Then if that's true, you look at the adjacent sides, or sides that are right next to each other, and see if those are perpendicular, because perpendicular means they're forming right angles, and we know that all rectangles have 4 right angles. All right, so again, you can kind of visualize on the graph, we got a quadrilateral. This time it's JKLM. All right, and we start with looking at their slopes to see if we have opposite sides parallel. So do JK and LM have equal slopes? If so, then they're parallel. And do KL and JM have equal slopes? Because that would make them parallel. So if that checks out, we know we've got a parallelogram. Then we can look and see, is it also a rectangle? And that's where you look at the adjacent sides. Do JK and KL have perpendicular slopes that they're forming right angles? Same thing for JK and JM. Those are adjacent sides. Do those have slopes that are opposite reciprocals? And then same thing for LM and its 2 adjacent sides, KL and JM. If those adjacent sides have slopes that are opposite reciprocals, that shows they're perpendicular and forming 4 right angles, which makes the parallelogram a rectangle. So again, we could go through this example in class when we're together next. You may have a problem like it on homework and future practice, quizzes, tests, all of that. So this is just expanding those properties of rectangles and applying them to a proof on the coordinate plane. And that is the end of our lesson on rectangles. A little bit shorter than parallelograms because we don't have to repeat proving all those properties of parallelograms. But of course we can use those properties of parallelograms to help check things and solve things in rectangles, because rectangles are one of those first subcategories of parallelograms. So I hope you're enjoying building our quadrilateral family tree. Make sure that you worked out these examples in your notes, at least the park and the dodgeball field examples. If you want to try the coordinate proof examples, great. If not, we will practice those together in class when we're together next. Also, be looking for the silly phrase during the lesson. You know, I will ask if you caught that or not as you watch the lesson, and make sure that you saw the whole thing. All right, see you guys next time.